continue discussion on graph cut. I'll talk about a paper that is a classic paper on graph cut by Borkov. Oh, handwriting is too horrible. Anyway, they have this paper, it's 2001, basically a classic paper that got over 2,000 citations. And okay, last time you see like we trying to do graph cut, and then just if you remember, like, we are only separating like inside and outside is also like only for basically 1D, not 1D, but the labels can basically you can consider we are having a label can only have like two values, 0 and 1, so it's not very general. And in this paper, they consider much more general problem. Basically, if you have this kind of problem, you kind of encounter quite often. Basically, you have a energy function we want to minimize. So some kind of energy function. So and energy function basically have two components. One component is just the local energy that maybe I can say like from the data, and then there's some smoothing parts that are because of the labor. So F is basically a labeling function. So basically you have, for example, 1D or 2D, is you have an image, you are trying to, let's say, for each pixel, you want to, okay, let's just give a more concrete example. Let's say you want to do disparity estimation. And then you have two images, and you want to find out like what's the disparity of this versus this, and so on. Then basically disparity will be like this pixel is shifted by that much amount, right? And if I have this for each pixel here, let's say I have this pixel here, and it is shifted by that much to, draw too well. Then I say like this much is the disparity. And then you can think of this as a label, right? Essentially for each pixel, you have a different disparity. And depends on these two images, if the two, let's say, two block surrounding of this pixel is more similar, then you can claim the energy is smaller, right? So this energy thing, this energy probably I should say, this energy thing you can consider as, let's say, just mean square error, for example. And then the smoothing part will be like you want to have not the disparity just change rapidly. So in the sense that you want to, let's say, for if you have what was I saying? Yeah. I guess I explained it that way, unless you don't really understand what I mean. So then the smoothing function, for example, like this smoothing can be written as, let's say, more concretely, just some energy function between two pixels, that's a PQ, that PQ is the labeling pixel. So I just write this as the label, to indicate that PQ is a label. And then like FP, FQ, let's say. So then, for example, like I can have this energy part like this matching as, for example, just the distance between FP and FQ, something like. Then I basically will just force the labels to be more similar, tends to be like more similar than more, I shouldn't say similar, but like less amount of variation. And for this data, let's say I can write it as like P here, and P also. So P. So essentially my energy function is something like that. So my goal is really want to find this energy function F here. Not energy function, so find this labeling function F here, so that the energy function is minimized. So this is okay. So if you're not familiar with this, it's just some kind of minimization that you want to. If you just look at this as some kind of local information that you want to also make sure.
That one is for the e-data, is the BP or is DP?
This is.
No, the first one. Oh, okay.
Well, it's just some kind of quotation. So okay, this is our objective. So you can map into lots of problem, or like you can even just consider this as a pulse model. Actually, this is basically pulse model. There's an extension of the AC model. So now how do we, okay, this is basically a combinatorial problem that is actually quite difficult to solve. You can have lots of ways to solve it. Like, okay, we try to minimize, basically minimize over F here. One way is, for example, you can even use BP to solve this, but it will not do quite well because there are lots of connections. So if you use loop BP, basically the convergence probably will be very good. And you can use maybe simulated annealing, for example. But it turns out if you use GraphCut, it will be much faster. Basically, from the paper, they have results that in terms of like convergence times, they're like way ahead. Like this is the minimum energy found, and then like compare with like simulated annealing, this will be like simulated annealing will be like way far away. And this is an exponential plot and that. So therefore, like this really become a standard way of solving this kind of problem. So before I continue, I just want to make sure that any question just about the setup. So the setup is basically a simple optimization problem. Yes.
PQ is in a long set.
PQ is a pixels, basically. You can think of pixel, for example. So P is like all pixel, PQ is all pixel. This is labels.
In a big block, you mean? A shift root
it
path.
can be 1D, 2D, or 3D, or whatever. So, for example, it's 2D, it would be like this. So each pixel, P, this would be like, the set of P would be all pixels in the image.
Oh, you said all the image.
Yes, the entire image. It's not just a block. And like this would be like sum of all the label in pixels.
D is some function, some.
D is some function, yes. Is yeah.
Non-negative.
Yes, it should be non-negative. For this to work, it should be non-negative. Like this. Okay. So now, basically, the paper proposed two algorithms, like they call it alpha beta swapping and like alpha expansion. So basically, the idea is let's say let's just talk about what they mean by alpha beta swapping. So let's say you already have an image now, And then let's say you have a labeling now. Is let's say this part is 1 and this part is 2, this part is 3 and so on, this part is 4, let's say, and this part is 5. Then an alpha beta swapping step is basically just like you swap one of the label to another label. Let's say I swap this 1 and 2 so that I will get into an image, like new labeling function that, let's say, like this. So this is an alpha beta swapping. So basically just swap some labels. And they have this alpha expansion. Is basically you have again like some label. Let's say this is 1, this is 2 and 3 and 4, 5. Let's say, and for alpha expansion, let's say alpha expansion over this label 1, I will just try to expand the territory of this one label here. Maybe you will invade the other parts. Let's say you have more than 1 here. Let's say. That's the alpha expansion and alpha beta swapping.
For swapping, it's based on the pixel or based on the area?
For each pixel, you have a labeling, right? Basically, let's say for each pixel, I have a label. And then, like, let's say originally, like this whole area is labeled as 2, and this whole area is labeled as 1. And then when I swap, basically I would just say now this will become, the whole area become 2 and this whole area become 1. So we swap that. So there are basically what they propose is algorithms using GraphQL to solve this intermediate subproblem. So basically you're trying to optimize this thing here, the big thing here. The strategy is like as follows. Let's say you have the original labeling method like this, and then it will just look at each label. Let's say like look at 1, and then look at 2 and say, should I swap it or not swap it? Okay, wait. I guess I made a mistake here. Oh, okay. I guess I made a mistake. I'm sorry. So when I say swapping, okay, this what I want to say, okay, if I swap, I'm not just like swap the whole area 1 to 2, but basically in this 1 to 2 part, I reassign it basically. So this 1, maybe part of it now can become 2, and then there's part of it still 1, and then maybe I have some 2 invade here, and then I have some 1 that go into 2 territories like this. So this is the swapping. Then basically the algorithm is just, okay, assume like now I just consider 1 and 2. Let's find the optimal swapping. So I just want to make sure like I will find the best mapping, best labeling, such that after swapping it's like the best over all the possible swapping. And then they will just keep doing each pair of labels. So let's say I start with 1 and 2, I think this is like optimum. Then I'll go to 2 to 3, let's say. And then I swap again, like say like 2 to 3 now maybe. Then some of this 3 become 2, let's say, and then like maybe this whole thing become 3. And we just continue like maybe I should say 1 and 2, and then maybe 1 to 3, and then 1 to 4, and 1 to 5, and look like that. And then I will 2 to 3, 2 to 1, and so on. So if there's nothing like it cannot improve after all this combination of swapping, then it just stop. So that's the method. So what they propose is really the GraphQL algorithms to solve this intermediate step, like these sub-steps here. Of course, for alpha expansion is similar. So for alpha expansion, you will just for each of these label, you try to expand them. So like you go for the first one and see like, okay, maybe one can, like this energy function can get smaller if like one expand to be like this, and then I get to 2 and I try to expand 2, maybe like it get invaded to here, and then actually I get lower energy, and then like I go to 3 and so on, and then like eventually, if I cannot get a smaller energy, then I will just stop. So that's the.
Excuse me, what's the advantage of this, for example, swapping on the expand?
Actually, there's no advantage for swapping. The swapping, okay, I need to get into a little bit detail. The swapping is a bit more general in the sense that for alpha expansion, you need an assumption. You need to assume like VPQ. This thing is a metric. So metric in the sense that in particular, you need to solve, you need to satisfy the triangle inequality. So basically, I need to make sure I have V, P, R plus V, R, Q is bigger than equal to V, P, Q, something like this. You will see why I need this condition, and for this alpha beta swapping, I don't need that. So, but you see that I will need more integration for alpha beta swapping actually. And of course, for both cases, it doesn't necessarily get you to the global optimum. But if there's nothing you can get better for this substep, you can pretty sure you are in a good local optimum. So.
And when, when, for example, swapping with the stop.
Okay, swapping with stop again, like, it's just like that one. Right? You just, if you try everything, you don't get better, then you stop. Like you look through all these pairs and you basically not swap anymore, then you just stop.
When you don't have any changes.
Yeah.
And also for this one.
Yeah, also for this one, if you can't have any expansion like for all the.
All area have same value.
Same.
No.
Not
Either
same
one.
value.
Same label.
Oh,
You
oh,
mean the
labels,
same
like
label?
this is a label.
You mean
So
the
for
label?
example, this thing is like the label.
All of them
In the
one.
sense that for all this, when I put one here, all this pixel here, for a pixel, let's say this pixel P here, this FP is equal to 1. That's basically what I need.
All the pixels
Yeah, in this here. Everything here is like F, this thing is 1.
is equal 1.
Yes,
Yes.
this
Is
F pixels here is equal to 2.
Equal to.
So, okay, let's write
I
this.
think all equal to 1.
Let me write an example like
No,
this.
all of, because it's the labeling, all of them, the one, the label one, all of them is one.
Let's just write a small example here. So let's say this is like, let's say this are pixels, right? This is all pixels, and let's say this is like equal to. So what I care is like the total energy, right? And let's say I have this precisely like let's say I have just 2 kind of labels like 1 and 2. So V1, 2 will be equal to 1. Let's say V2, 1 is also equal to 1, and then let's say V1, 1 is equal to V2, 2 is equal to 0, something like that. So let's say I have a labeling like this. Let's say this pixels here is area 1, this pixels here is area 2. And they have some local function here that this. Okay, here I assume that for each pair that is constant, right? of course, you can actually make it very general that like for every pair PQ, they have a different kind of smoothing function, smoothing energy function. But in general, I don't think that really necessary. So here I just assume that for every pair, it's the same function here, let's say. And then like I have this pixel, let's say dp. So also like you have some big, I mean based on your observation, maybe you have like this pixel dp1 is equal to 1, let's say dp2 is equal to 2, something like. Maybe you have a different dp here, like dp1 equal to 10, dp2 equal to 2, let's say stuff like that, right? So what I want is I want to find the minimum of all this sum. The sum is like I have like sum of all this 9 dp here, and also like I have this like 2, 3, 4, 5, 6, 12 edges here, right? I need to sum over this all this p here. So let's say then okay, the dp part seems very easy, right? Like obvious, right? So the edges will be like for example, if I have the v function is like this, I won't have contribution for this smoothing energy only at the boundary here, right? So I will have this 1, 1, 1, 1 here. So you can see that if my labeling is more fashion, for example, if I have 1, this label as 2, and this label at 1, this label is at 2, label at 1, label at 2, 1, 2, 1, let's say, then I will have like much larger contribution. I need to sum for this edge, sum for this and this and this. So I will have basically equal to, just the smoothing path will be equal to 12. Yeah, so yes, okay. Okay, that is pretty clear now, right? So anyway, then, okay, if it's very clear, then we can go into these sub-steps, basically, how to really get the optimum swapping and the half expansion. So we'll start with the swapping. So basically,
Age is the boundary. Age. Age.
edge is a boundary.
Yeah, you said the edge. Edge is the boundary.
Oh,
The
okay.
label.
Well, when I say boundary, it's like a boundary between different labels.
Yeah.
Oh, no.
No.
I don't think edge is counted as boundary. Yeah, unless you want to, but yeah. Of course, it depends on your problem, right? Because you can always set it up to have edge as boundaries also. Maybe you can just hook up some more, but yeah, we can talk about that. But yeah, let's assume that they are not boundaries first. So okay, let's go for alpha expansion first. Alpha beta swapping. Alpha beta swapping. So let me just. Okay, the idea is quite simple. So not yeah, I shouldn't say simple. I mean the idea is actually intuitive, but it's quite genius to think of how to do it. So basically, is you think of if you have a swapping, what we need to do is really try to map the mean cut. Map the swapping problem to this mean cut problem, right? And to make sure that the mean cut solution will correspond to a swapping solution. And basically, in the sense that for every possible cut, it should be correspond to any possible swapping. And also the best cut, basically the mean cut, will be correspond to the swapping that have minimum energy. So So it's easy to say, but so you need to have some, to be quite careful to think of that. I guess I should keep the, okay, I'm not sure how to keep this original thing here. Let's say dp alpha. Let's say I have some over dp, and this is for fp, it's p, and p here, and so on for all the labelings. pq here, not labeling, labels. pq here that I have this function is p. Okay, let's drop this pq. This will be a lot of handwriting. Let's say p pq fp fq here. So first of all, we only consider the alpha beta part. In the sense that there's lots of labels, right? Remember, these are the labels. And some of these pixels will have labels alpha, and some of these pixels will not have labels alpha and beta. Let's say we start with, as we draw there, we start with one labeling that well, let's just look at this part first. Right? I can split this into like some pixel that will be, let's say if we have notation for that one, okay, they have a notation for that one is p alpha beta, that's corresponding to the set of pixels that is, they have labels alpha and beta for the moment. So that means that if we have this, this is alpha, this is beta, this is something else, and this p alpha beta are all this pixel here. And of course I can split this dpfp as like p that is not in this alpha beta there, dpfp there. And of course like this part I don't care, right? It doesn't do anything for the moment if I restrict myself only consider alpha and beta trying to swap them. So and this will be something like, also it will have only when both of them are in alpha beta, so I have a p and q is a label, and also p q is both in p alpha beta, and then this thing here p q, and I have something else that I don't care. More or less like this, I guess. So the idea is that I need to absorb this into a graph, and it turns out the cut will be correspond to these terms here. I guess it's easy to write it down before I say everything first. So let me write down an example that used in the paper. Let's say P, Q, these are the pixels, that's W, and there's some note here, there's an R and an S here, and it's beta of the note. is beta. So this is T. Alpha T beta. And I have an edge here is B S. So the value of the edges are given here.
Excuse me, RS is the same as alpha beta?
RS
the
is
pixel
the
or-
same. No, okay, these are pixels. So P, Q, W, R, S are pixels, and I haven't mentioned it yet, but these pixels are, okay, these are in P alpha beta. So apparently, like, I don't care about pixels that's outside this alpha and beta, right? So I only grab pixels that in alpha beta, and I put all the nodes here. And I found edges here is basically have this T, for each node is connected to this so-called alpha node, and this node is some beta node here. And okay, let me give some names here. So we call this like T edges here. Actually, we call it T links. T links, let's call it T links. T links, and that's this. We call it N links here. So basically, if like PQ is a label of each other, then I will add an N link there. If they are label, if they're label of each other, and the weight of that edge will be given by this one, PQ alpha beta. Wait a second, is that correct here? Yeah, I think it's correct. Okay.
And what's the
Yes.
what's the age between alpha and the pixels, or beta and the pixels? Is it EV?
Say it again.
What's the age between alpha, beta, and the pixel?
Yes, that will be from alpha node to here to a pixel will be like TR alpha. The TR alpha is given by here. Like TP alpha will be something like that. And TP beta is something like that. Okay, honestly, it's kind of hard to give a very intuitive explanation on this, but apparently what he's trying to do is like really, okay, maybe I explain this first, it will be easier to see. So, okay, what happens if I do a cut on this graph here? If I do a cut, I have to cut for one of the key length. For each pixel, I have to cut for exactly one of the key length. It's quite apparent, right? I cannot have an otherwise. I mean, I can only cut for this, or like cut for this, or cut for this, or cut for this. But I have to cut for either one of these, and not both. And you can see that for each cut, therefore, actually map to a solution. If I say like, if the link is cut for, then I will say, let's say the link that connecting to the terminal beta is cut for, then I would say this pixel will map to beta. And if it's like cut for alpha, it will map to alpha. So therefore, like each card will basically have a mapping for a new swapping of all these pixels that is inside this alpha beta region. Now the only thing you need to visualize is how each of these cards will turn out map to this function here, right? If each of the cards is exactly mapped to one function, Actually, it turns out it's not exactly mapped to this function, but it mapped to a function plus constant. So therefore, it doesn't matter, right? Because constant is okay. So then, of course, if it's one-one mapping, then the mean cut will just get us the minimum solution here. So let's see. Okay, let's try some simple case maybe to help. So one thing is, let me just denote this C as like for any cut here, that's the value of the cut. This C will compose of basically I can write this as C intersect with what I've just written down is basically just, let's say if you have a cut, any cut here, then I can kind of like count the value of cuts through, consider each part like separately, right? I can count like how much contribution for the cut for this first piece of segment, let's say. And then how much contribution for this second piece of this segment here. So on. So the first piece of segment will be like this, like each of these vertical segment will be like the terms over here, right?
What's C?
C is a cut.
Oh, it's a cut.
So a cut will be, okay, basically when I say C here is a cut, C more precisely should be including, let's say for this particular cut here, C will be like, is equal to a set that include this edge, this edge and this edge and this edge, this edge as element. So therefore, let's see intersect with this, and my computer value will basically just the value here, and this value is here. So let's see, just look at this thing for example. That was this thing here in general. Let's see if we can.
set again?
No, E is not a set. E now is the edge of this here. So ERS is this edge here. So if I just basically this is the EPQ here.
Okay, okay.
So that would be a number of different cases, right? I mean, this can be like several different values. Either you cut it full, then if you cut it full, you have some values, right? So if I get to cut it full, then okay, actually maybe I can draw this. Okay, draw it. So this corresponds to cutting it full. I'm not sure you can imagine what I'm drawing. Or like it can be this case or this case, right? This are the C here. So if I'm in this case, then basically it should be 0, right? I don't cut through it. The set is empty, so therefore it's 0. If I cut through it, then the values is this V3 Q alpha beta here. But on the other hand, when I don't cut through it, what does that mean? What does it mean? When I don't cut through it, it's either this K or this K will correspond to both this label is yeah, it's the same way. Both of them is back to the same label. So therefore, like this contribution, this V, P, Q, C, oh sorry, so C, F, P, F, Q will be equal to 0 also, right? For these cases, because FP now is equal to FQ. So actually, in general, I can just say this is equal to V, P, Q, F, P, FQ, right? Yeah, because if I cut through it, then that one of them will be alpha, one of them will be beta. So either way is just, so therefore this is just equal to this. And let's see. And this is quite simple, right? Actually, this is like I either cut through this, I mean, if I cut this, either cut this lower one or cut through the higher one. And then in either case, it will be this term here. Like, or like, I mean, this term or this term here. And so, therefore, I should have I don't think this helps too much now, because I can just erase it. So I should have this C is just continuing from here, should be equal to sum over P alpha beta, and this will be that term here, D P, that is basic. Okay, actually, this summarized is just equal to D P F P, right, plus Q over M P Q dot P alpha beta V P Q F P F Q. So I can have this P alpha beta over Q M P. Oh, sorry, that's no MP. Yeah, I don't think that's an MP. Oh, okay, yeah, that's something. Oh, MP means the neighborhood of P. Okay, that's right. Q is MP. alpha, beta, PQ, PFQ. Okay. That's the first term. And now I have the second term is like PQ and it's neighborhood. And PQ in P alpha beta. V PQ and PFQ. So I hope you see what's important is this basically include all the terms here that's relevant. I mean, to alpha beta. Of course, it doesn't include all the terms, for example, these terms here. But it's not relevant because I'm just trying to optimize only for the labels, pixels that currently have labels alpha or beta. And therefore, for me, it's not relevant. And basically, this thing pick up all the terms that is supposed to related to alpha and beta, the pixels that inside alpha or beta. Therefore, if you do a cut, this will just map this problem exactly. So the minimum cut will also correspond to the minimum labeling for the swapping of alpha beta. And of course, then you just continue, like you have another alpha beta, then you have another alpha beta and so on. But okay, this is for the alpha beta swapping, and this. Actually, honestly, it's not too easy to seal it, but we probably one more step or two before we can get this. This clear enough. But okay. Any question? Besides that, you may want to get more into comparing. Okay, this terms apparently is fine. This part. So for that part, maybe need to. Let's see. Actually, if I can convince myself. So I have. This is some P that in alpha beta, and there's some Q in the neighborhood. Actually, Q is not in P alpha beta, and this is like some P and Q both in the neighborhood. No, not I mean both of them inside the P alpha beta, and
for the second thing, Q is only the neighbor of P, but not in the alpha beta.
Say that again.
For the second summation,
Yeah.
Q is in the neighbor of P.
Wait, you mean this?
Yeah.
This one? Yeah. Q is the neighborhood of P, but not in the P alpha beta region.
Okay. If we consider boundary between the alpha beta, there is a shared boundary that alpha beta are neighbor, and there is another boundary that it's between, for example, alpha and the others. This term, one of first one.
For example, let's say an example would be that you have a P here, have a Q here, and you have an R here, let's say. And then let's say this is originally alpha, that's originally beta, and this is originally gamma. That's outside, you have pixel here. And then you have this term is summing up the edge here, like for this pixel connected to this pixel, just originally is not in alpha beta. So this is the alpha beta area. Let's say, actually more precisely, this is the beta area, this is the alpha area, and this is outside. And then of course you have this, and then there's some more pixels like that. So the thing is, I think of that, the terms here that is related to the alpha beta will be the term inside this alpha beta, right? Alpha and beta. But also, when you swap this alpha beta, you affect the boundary also, right? You take into account. And that is picked up by this term here. And my point is actually, if you think a little bit more now, I see, like you pick up everything, right? Because you look at any pixel in this alpha beta, and then you consider some of basically all the neighborhood, because if for a pixel, either it is inside alpha beta, P alpha beta, or like outside P alpha beta. Okay. Inside P alpha beta will be taken care of here. Outside will be taken care of here. So therefore, like every terms here that like is relevant for this swapping will be included. So I guess this now is clear enough. So this is the alpha beta swapping. Let me do not take too much more time and talk about alpha expansion. So alpha expansion is actually more complicated. Okay, in a sense it's more complicated, it's also more elegant because it's exactly, the cut is exactly correspond to the solution. So have an alpha expansion. So again, the alpha expansion is trying to expand one of the label, the territory of one of the label. Okay, let me just, again, I just draw the graph first, and then it's probably easier to explain. So I have, again, some alpha nodes here, and I have some P nodes here, some Q nodes here, and there's some R nodes here. So, I mean, nodes mean pixels here, S pixels here. So these squares are pixels, and let's say originally this is a label as alpha, and this is labeled as 1, and this is labeled as 2 here. So this is labeled as 2 here. So again, I have some edges going from this alpha node, and some edges from this beta nodes here. And then actually it doesn't call it beta, we call it alpha half nodes. That's alpha bar node. That's there. So I guess that's the alpha bar node. And this, okay, I can just call it T as alpha. And this now we call it T as alpha bar. And what's again, like if we have connection, I mean, if we have two pixels labeling to each other, then we'll add an edge there, and the edge will be can EQ out here, just a little S. So, and what's more is that if I have labeling node against if this is a labeling node, but if currently if it's not have the same, if they do not have the same label, like for example this one label 1, this has a label 2, then I will add an auxiliary node here, like let's just call it A here, and also like because this have different labels, this is currently R is labeled as 2 and S is labeled as alpha. I introduce another node here, say B, let's say, and then I will connect M. And I will also connect A to here, to the alpha bar node here. And so these edges, I will just call it like E, R, B, and this will be E, B, S, and so on. And this will be, all this will be T, like T, alpha bar, B, let's say. And let me draw down the weight also, and I'll explain something. P alpha bar is infinity. P alpha, P alpha bar is equal to P FP. P is now P alpha. Yeah, I will just drop the PQ right now because to worry. P alpha, B F alpha FQ. This is E AQ. B FQ. T A alpha bar. This is like if the P and Q are labeled of each other, but FP is not equal to FQ. And if P and Q are labeled to each other, but FP equal to FQ, then this EPQ is just use VP, FPFQ. Actually, there's a typo in the paper. Anyway, so okay, you immediately see why you need the triangle inequality. So basically, remember we have the triangle inequality we have to satisfy. That basically we have P alpha plus V alpha FQ has to be bigger than equal to V FP FQ. Actually, I guess real implementation is to become safer to just say it should be bigger. So now what you see is like, what's these edges here? This is the EPA, right? EPA is corresponding to V FP alpha. This is DAQ is like V alpha FQ. This is basically the V FP FQ. So because of the triangle inequality, you see that like I cannot have cut like this. If not, it's not I cannot have cut like this, but if I have the mean cut solution cannot cut like this way, because I can always, for example, if the final cut is like this, apparently I can get better cut if I cut through this instead, because some of this is bigger than this here. So and that's why you need this triangle inequality for this to work. And also like if you look at this carefully, basically, okay, I guess it's convenient also. We'll summarize these three edges here as a set. Use big E here, E PQ here. So basically, this we just cluster these three edges to call this EPQ here, keeping PQ here. So what happens is that if I consider the, let's say C is the mean cut, apparently, right, if it intersects, if EPQ here, it can only cover one of these edge here, one of the edge here, one of the length here, because what I just said.
Yes.
No, exactly one of them. I mean, I can only cut like this or this. It cannot cut like this. Yeah. So I'm actually let's look at what is this exactly. Yeah. What's this? Okay, I guess I can list the possibility again. I can cut, let's say this is PQ and stuff like that, right? I can cut this. If I cut this, that will be just FP, FQ, right? So I can cut this. If I cut this, it's basically V FP FQ plus what's that? Oh, okay. Actually, no. I made a mistake also. What I just said at the beginning is correct. I cannot cut for this also. Let's see.
Yeah, you can.
It's not possible because this will get me smaller.
Yeah.
Oh, this one.
Yeah. I mean, yeah. I shouldn't cut for this if this is my minimum cut. So therefore, like what
that one is the same as this one. If you want
what I mean is that for example,
yeah, the
let's
next
yes.
edge.
Yes. Let's say this cut here. This is not the mean cut because I should shift this to here and get a smaller cut. So what I originally said is correct, that it can only cover one of these edges in this set here.
Excuse me, you put node A and B between all of the nodes?
No, it only between nodes that the pixels that currently have different labels.
Okay. Yeah. Okay.
And but if we put it like that, then basically you see that I can cover this or I can cover this. If I cover this, it's basically have to give me this FP alpha here. And if I cover this, it will give me B alpha FQ here. Again, I can summarize that, right? Because, okay, I didn't say it yet, but again, like this, if I have a cut here, this cut will always, okay, this again I call it key length here for the pixel. For each pixel, it will, again, an either or thing, right? It has to pass one of the key length, one and only one. And again, I can use this as to map to a solution of the labeling, right? So if I cut through the upper one, then it will just map to alpha again. But if I cut through the lower one, then okay, actually, if I cut through the lower one, then I will keep the original label of the. So, and then if you look at that, if I cut through this side, what does it mean? You cut through here, on this side here, that's actually, it means that like P should keep the original label. No, actually, if I cut through this, and I cut through this. Oh yeah, actually, what I can say if I cut through this, yeah.
The last picture is not correct. The last one. It can be either bottom.
Oh yes, sure, you're right. Yeah, this is.
Because if
It's just
we
like
have something
if the
in
direction
bottom,
is not
we
good,
have to
yeah, this has to be like
Yeah.
this, yes. Right. So, okay, yeah. Yes. Then I guess I can draw some this here also. So for this case, basically, of course it will cut through this FP here, but it also implies it will cut through this here, right? So it cuts through this here, it means that like for this pixel Q here, it will map to alpha, right? So therefore, like actually, Q will be just equal to F alpha, alpha will be just equal to FQ. And similarly for this one, if I cut like this, I basically, this P here will cut through this link to go to alpha. So again, FP in that case will be equal to alpha. So therefore this should be FP, this should be FQ. So again, this can be basically grouped together as it's just generalized to be FP, FQ here. And what else? So how about edges that does not have a, okay, maybe this edge here. For edge that originally have the same label, again, like last time, like let's say consider this C intersect with this EQR here. So this QR basically is labeled to each other, but basically they have the same label. FQ is equal to FR. So therefore, it doesn't have an auxiliary node in the middle. And for this one, what is this? Okay, again, like several cases. Either you have this QR here, QR, let's say. You can cut like this, or you cut like this, or this way.
What's the second one? Oh, okay.
Yeah. So this is the C here, C here. Again, for this will be just equal to what's that? Like EQR is equal to here. It's equal to just VF QFR. Oh, sorry, so bad. I say something that doesn't even write the same thing. VF QFR.
Yeah.
And for this will be 0, right? Basically, it doesn't cut through this line, therefore it should be 0.
Yes.
But again, like if it doesn't cut through it, that actually basically means that like for both of this label, you are sharing this after the cut is still sharing the same. Both of this pixel they will share the same labels, and therefore like the V between these two labels will be just equal to 0. So for this case, actually for both cases, the V, FQ, FR is equal to 0. Right? So again, like this will be like generalized to be FQ, FR. So, okay, now actually we consider this set and only thing left is this set, right? And like, let's consider C intersect with T P alpha and T P alpha bar, let's say. So I can cut above or cut below, but that's very simple, right? If I cut below, if I cut above, then alpha will be just equal to, or like I should say, that pixel should just map to alpha, right? So therefore, like alpha will be equal to FP there.
Rounded up.
Let me just draw the cases again. So let's say I have 2 here, this alpha bar here. So if I cut here, so what do I have? If I cut here,
That's just the dp of alpha.
yeah, there's a dp alpha, right?
Yeah.
dp of alpha. If I cut here, I will have like dp of fp here. But if I cut here, basically, I'm saying that like p should map to alpha, right?
Yeah.
So therefore, like in this case, actually alpha is equal to fp, right? Because like, we are claiming now the link,
It means we expand the alpha.
Yes, remember
The
like
label we change.
when we
Yeah.
make a cut here, we are basically mapped to a solution. When we cut above, we are saying that like we should have the pixel to label to alpha. If we cut below, it will just have the previous labels. So therefore, like since we are cutting above, then alpha should be equal to fp.
Is it, I think why for the second one is the dpfp.
Oh, okay. If you cut to below, you are not changing anything.
Yeah.
Yeah. So the originally is fp is still fp, right? What I mean is you have a pixel with an image here. The alpha expression is like you have all this pixel, you are going to get a bigger territory, right?
Yeah.
So let's say you have a pixel here, is p here. So that will be 2 cases, right? Either now you become alpha. If you get invaded by this alpha thing, then now your fp will become alpha, right?
Yes.
Or like if doesn't get invaded, then your p there will be still, your label there will still be fp, right? So nothing change. So therefore, I guess in some way it would still get like dp fp there.
Yes.
So therefore, that we have all 3 components now. So I can write here C D P Q is equal to V F P F Q C D P Q, or like QR anyway. V F P F Q. So therefore the C there would be just equal to C sum over all the individual contribution, right? You sum over all the P here for all the pixels here that C intercept with like TP alpha, TP alpha bar plus sum over each of these pairs here, that's basically this PQ, the PQ FP is not equal to FQ, and PQ is neighborhood of each other, that will contribute this set EPQ here, and plus a symbol for PQ. Again, it's in the neighborhood, but like FP is equal to FQ. Let's see if the set will then of course like this is just equal to, this term is just equal to dpfp, and these two terms is just equal to bfpfq, and of course like this you consider both when the pair is of the same label and also not in the same label, is basically consider all the pairs. So therefore, like, just it's basically equal to the original function there. And that's basically the expansion. So have any questions? So it's kind of nice, if you write a paper like this, you will get like 20,000 citations.
But not for this one, for the journal version. It has 3,070 something. There's the PAMI for 2001. This one is a 1999.
Yes, this is 2000. I'm talking about the 2001.
Yeah.
Yes. The 1999, I think is 300 something. This is
Okay, for our problem, for the disparity map, we can map the each each pixel, and our label is our disparity.
Basically, you just need to get all these energy function, right? You just need to assign the function. So basically, you need to, I guess they have standard way to do that, like how for B, I guess you will have to track, but I will assume maybe you can, I don't know what's the optimal way honestly, but maybe you can just do a first normal, and for these edges you will have the function, it can be just minimizing the similarity, right? So it can be like you have, for example, let's say you have for each pixel here, let's say this is a pixel, and then you have two images here. Let's say this is this pixel. I'm supposed to shift by this one. This is this part, and of course I don't know how big I should shift, right? So let's say I have a range for me. Like I say I have like from 1 to big D so many, right? Or like actually 0. Maybe there's no shifting. You always like assume that shifting in this direction, but of course you can do two ways, right? And then like for each shift you can just like compare the similarity, right? So you can like for each of them like you can just compute the mean square error for the block, and then take it as the energy function, right? The simplest case. Then you will have like this dp function, right? This d for this pixel p here, you have this dp that can take value from 1 to d basically. But I guess you need to check what do they do some. For example, you can put an exponential on the mean square or something like that. It depends on like, I guess people want to try it out, like what kind of energy function is best to in representing this kind of problem.
And another question: how about the occluded area, and we don't have the movement?
I guess you need to check also.
Yeah, maybe we can assign label
But you can have a
minus
special
1.
labels, right? Yeah.
Yeah, and after that expand the neighbor areas to cover the.
But I think DC used another way for letter.
Okay, but do you have any other questions like besides the? Some concrete questions.
And another thing they said that about the restoration, and for restoration they said that they use the intensity instead of the reflection.
Yes, but unless from here, yeah, maybe just.